All right, so we are now moving on to the climate change section of the course. And this course so far has been mostly about discussion, and it will continue to mostly be discussion. But when we first met, some students said that they would like to see something a little more technical, and I thought this would be a good place to introduce something slightly more technical than what we've been looking at so far. So, you've been looking in your macroeconomics course at growth models like the Ramsey model or the neoclassical growth model. So, the model we're going to look at next time we meet is one by Bill Nordhaus, the DICE model, which I'm blanking out on what the acronym stands for, but it's a very popular model in climate economics, and it's actually used by um, the International Panel on Climate Change and other big famous organizations in order to calculate the way that the climate interacts with the economy, and then also to sort of solve for optimal policies in terms of taxation. Uh, so anyway, since it's something you're looking at and it's something a little bit more technical, I thought this would be a nice thing to add. So I changed the reading up a little bit, and now the main reading I want you to do actually is more or less just a bit of the manual actually that is put out for this DICE model. Okay, so the current version is actually 2016, I think. So there's one small update, but I kind of looked through it and it didn't change very many of these equations. It's mostly just a change in the parameters that they put in relative to the 2013 model. So it still works in the same way. Okay, so I don't want to go into the details here, but what I want you to kind of do when you're reading this is to kind of look at each of these equations and try to understand what it's saying. Okay, so you can see here, this is like a social welfare function. Okay, so we're summing from 1 to some maximum time, so let's say 500 years. Bug floating around here. And you can see it's got this very standard macroeconomics flavor. We've got a utility function that depends on consumption and labor. And then R here is a discount factor or discount rate. Okay, so down here, look, we've got a CRRA utility, and we're multiplying times the number of people in the population at any given time. So you can see that this is just all fairly standard macroeconomic stuff. But there's going to be a twist, of course, because we want to put the climate in somehow. So when you get down here to the production function, this Q here is going to be output. Now, if you look inside, we've got capital, we've got labor, it's Cobb-Douglas. We're multiplying by a TFP, all pretty standard stuff that you're seeing in your macro course. But now we're also going to have these two extra terms. We're dividing by 1 plus omega, and we're multiplying by 1 minus lambda. So the bigger is omega, and the bigger is lambda. You can see that the lower is output. Okay, so that's going to be the climate. That's how we're going to put climate into this, or climate change into this model. So you can imagine there's a damage you're going to get from having, too much climate change, and that's going to reduce output. Okay, and so on and so forth. So the model both has this economic component that we just talked about, and then when you get down far enough, it's going to also have a climate component. Okay, so the idea here is to kind of just look through this model, try to understand what each of these equations mean, and then we're going to talk about that during class. Okay. Second thing I posted is a link to a website. So this model is something you have to solve numerically, and I found a program you can use to do it on MATLAB, but since I think that most students probably don't have MATLAB on your computer, the only model that I could find where you could actually solve it and do what we want to do with it was a website, and it's based on the model from, not this version of the model, but an earlier version of the DICE model from 2010. Still has the same flavor though. So we're going to use that website to play with the parameters that you put into the model, and we're going to see the way that affects things like emission levels and optimal taxes and things like that. And then also, we're going to talk about the social cost of carbon. So we're going to think about, say, in a cost-benefit analysis, how much, how should we think about weighing, say, the cost of building a new rail network that would save carbon because people will ride the rails instead of ride the trains instead of taking their cars, versus the benefit we get from the reduction in carbon. What actual number should we plug in there? So yeah, that's the plan. I also posted a short YouTube video, kind of a cartoony video that explains this idea of the social cost of carbon. So yeah, that's what I'm planning on doing next time we meet. Talk to you then.